Some problems in computer science, they just feel solved, like set in stone a lifetime ago. The shortest path problem? That was definitely one of them. For over 60 years, we were pretty sure we had the fastest way figured out. Well, it turns out we were wrong. A brand new algorithm just completely shattered that long-standing speed limit. And today, we're going to break down exactly how they did it.
Look, every single time you pull up Google Maps or Waze, you are tapping into this exact problem. You ask for the fastest way to get from, say, your house to the airport, and bam! In milliseconds, it spits out the perfect route from a mind-boggling number of possibilities. The logic that powers that little bit of everyday magic, that's what we're digging into today.
All right, so here's our game plan. We'll kick things off with the classic problem and its reigning champ, an algorithm called Dijkstra's. Then we'll uncover its hidden weakness, its Achilles heel. And that's when we'll see how this new approach cleverly smashes two old-school methods together to create something incredible. And finally, we'll talk about why this is such a huge deal.
Okay, first things first, let's get specific about what we're actually talking about. This is the single source shortest path problem, or SSSP for short. The goal sounds simple, but it's incredibly powerful. If you start at one single point, let's call it point A, what is the absolute most efficient path to every single other point in the entire network? Now, for this specific problem, there has been one undisputed champion since 1959, Dijkstra's algorithm. For decades, this thing was considered the gold standard. It's the one taught in every computer science 101 class, and it's been the foundation for so much of the modern world.
So how does this legendary champ actually work? Well, at its heart, Dijkstra's is what you'd call greedy. And no, that's not an insult. It just means that at every single step, it makes the decision that looks best right at that moment. It's always asking itself one simple question. Of all the places I can get to but haven't visited yet, which one is the absolute closest to my original starting point? And then, it just goes there.
Let's actually walk through this. Imagine you're at the start. The algorithm checks out its immediate neighbors and notes how far away they are. It sees the yellow node as the closest. Great. It zips over there and locks in that path. That's final. Now, from this new spot, it checks out its neighbors. And if it finds a shorter way to reach them, it updates their distances. Now, here's the crucial part. It looks back at all the unvisited spots across the entire map and again picks the overall closest one. It just keeps doing this, over and over, until every single point has its perfect, shortest path.
And you know what's kind of wild? The paper that introduced this world-changing idea had this incredibly humble, understated title. You'd never guess that this simple note would go on to shape logistics, networking, and a million other things for more than half a century. It's just amazing.
But here's the thing. Even the greatest champions have a weakness. For all of its elegance, Dijkstra's has a fundamental bottleneck, a hidden speed limit that, until right now, no one had figured out how to consistently break.
So check this out. The very thing that makes the algorithm so powerful, always knowing the absolute closest place to go next, is also the source of its biggest problem. See, to know which point is the closest, it has to keep this huge, constantly changing, sorted list of every possible next step.
And that, right there, is the sorting barrier. That one step, find the next closest vertex, is at its heart a sorting problem. And when you have a massive network with millions of intersections, that list it has to sort becomes gigantic. This sorting step created a theoretical speed limit, which you see on screen, that for decades everyone just kind of accepted was the best we could ever do.
So how in the world do you get past a barrier that's been standing for 60 years? Well, the researchers here did something brilliant. They didn't invent some crazy new tool from scratch. No, they did something way more clever. They took two classic competing ideas and smashed them together.
The best way to think about it is like this. Dijkstra's is a sprinter. It's incredibly fast at making those quick, greedy decisions. But it gets totally bogged down sorting that massive list. Now, the other classic algorithm, Bellman-Ford, is a marathoner. It's way slower at each step because it methodically checks the distance of every single path in the network over and over. But it completely avoids the sorting problem.
So that just begs the question, right? Is there a way to get the best of both worlds? Could you possibly create some kind of hybrid that uses the sprinter's raw speed for the easy stuff and the marathoner's careful approach to dodge that huge, slow sorting job?
And as this new research shows, the answer is a huge, resounding yes. The secret sauce isn't just using both methods, but knowing exactly when and how to switch between them. And this brings us to the magic trick, the core innovation that makes this all possible. The researchers call it frontier reduction, and it uses a really cool concept called pivots, to totally outsmart the sorting problem that's plagued Dijkstra's for so long. To really get this, you have to picture what Dijkstra's is up against. It's staring at what we call a frontier, a potentially massive, totally chaotic collection of all the nodes it could possibly visit next. And it has to sort that entire messy list just to find the one single best place to go. It's a ton of work.
So here's the breakthrough idea. Instead of trying to sort that whole messy frontier, the new algorithm does something genius. It intelligently identifies a very, very small number of super important pivot points. It's like realizing that instead of mapping every single side street, you can get around way faster if you just focus on the main highway interchanges.
Okay, so here's the play-by-play. First, it lets the slow and steady marathoner, Bellman Ford, run for just a few laps. This is a brilliant move because it quickly solves all the easy, short-distance paths right at the edge. So what's left? The harder, long-distance routes. And the algorithm realizes that these long paths are almost certainly going to pass through one of those few major highway interchanges, our pivots. By finding these pivots, it can basically ignore all the little side streets and focus only on the highways. The massive search area shrinks to a tiny, manageable set, and that huge, expensive sorting job, it just disappears.
So, a faster algorithm sounds cool and all, but so what? Why does this actually matter in the real world? In this last part, let's explore what this new, faster speed limit really means for, well, everything.
And here it is, the new speed limit. Now, I know that formula looks a bit like alphabet soup, but here's all you really need to know. For really big, sprawling networks, like a roadmap with millions of intersections, but where each intersection only connects to a few streets, this new formula is provably mathematically faster than the old one. This isn't just a minor tweak, it's a fundamental upgrade to how we solve one of the most essential problems in all of computer science.
All right, so let's wrap this up. What are the big takeaways? First, an iconic, 60-year-old algorithm that almost everyone thought was perfect has just been beaten. Second, the solution wasn't some brand new invention, but a beautiful, clever combination of two old ideas. The key technique, the real breakthrough, is this idea of frontier reduction, using pivots to dodge that sorting bottleneck. And finally, this is a big one. It's a deterministic algorithm. That means it's a guaranteed, reliable improvement, not just a lucky guess.
And that leaves us with this one kind of amazing final thought. This breakthrough didn't come from faster computers or more processing power. It came from a fresh perspective on a very old problem. It really makes you wonder, doesn't it? What other fundamental problems that we all consider solved are just sitting there, waiting for one more clever idea to come along and change everything?